Welcome back. In this last segment, we're going to look at a second example of how to solve a LHRRC. In fact, I want you to go ahead and find the general solution to this recurrence relation using the algorithm, and then come back and check your answer here. Now, I hope you remembered that the first step is to check that this recurrence relation is actually linear homogeneous and has constant coefficients. Then you have to transform this recurrence relation into an equation and then convert that into a characteristic equation, which in this case is the following. Then you must solve this equation. Now in this case, the solution is not trivial, and again I encourage you to go back and review your algorithm for solving quadratic equations and make sure you get these two roots. So now you can use these two roots, of course, to write down the general form of the solutions, namely the solutions to this recurrence relation are of the form a sub n equals alpha 1 times the first root power n plus alpha 2 times the second root power n. And here the algorithm is applicable because the two roots are distinct. Remember, that's one of the conditions. So as always, remember that there's an infinite number of solutions if all you're given is a recurrence relation. How about if I give you also a set of initial conditions? So I want you to go ahead and find the specific unique solution for a sub n if the initial conditions are given as follows. A sub 0 is equal to 0, a sub 1 is equal to 1. And remember, this is the recurrence relation that is satisfied by the Fibonacci sequence. And since these are initial conditions for the Fibonacci sequence, your answer is going to be a closed form formula for the Fibonacci sequence, which might be a little bit surprising. So please come back when you have figured out the solution to this problem. Okay, so what you were supposed to do is to use these two initial conditions to determine the values of alpha 1 and alpha 2. So for n equals 0, you plug 0 in this general form and you get a sub 0 equals alpha 1 times this term power 0 becomes 1 plus alpha 2, and this term power 0 is also 1. And of course, a sub 0 is given as 0, so we get alpha 1 plus alpha 2 equals 0, which means alpha 1 equals minus alpha 2. That's our first equation. Now we have two unknowns, so we need a second equation which we obtained for n equals 1. So for n equals 1, we get a sub 1 equals alpha 1 times this root, power 1, plus alpha 2 times this root, also power 1. So here is the expression. Now a sub 1 is equal to 1, so this whole expression here must be equal to 1. And now we can use the fact that alpha 1 is equal to minus alpha 2, or in other words, alpha 2 is equal to minus alpha 1, so we can replace this alpha 2 by minus alpha 1. Then we can factor out the alpha 1 over 2, and what is left is 1 plus square root of 5 minus, and this became a minus, 1 minus square root of 5. So what's going to happen is 1 minus 1 cancel out, and minus square root of 5 becomes plus square root of 5. We have 2 square root of 5, and the 2 will cancel out, so we get alpha 1 times square root of 5. Now this number must be equal to 1, therefore alpha 1 must be 1 over square root of 5, and because of this equality, alpha 2 must be minus 1 over square root of 5. So now we determine the two unique values for alpha 1 and alpha 2. We can plug them back into this general form to get the unique solution, which again is a closed form formula for the Fibonacci sequence. And it looks like this. That's it. That's pretty complicated. So I will let you check that when you plug in the value 0 into this equation, you get 0. And when you plug in the value of 1 for n, you get the value 1. That is, you didn't make a mistake when you solved for alpha 1 and alpha 2. And finally, what I want you to do is to compute using this closed form formula the next value in the sequence, that is a sub 2. Now remember, this is a closed form formula for the Fibonacci sequence. So the next term in this sequence must be 1. So when we plug the value 2 for n in this expression, we get this term, and that must be equal to 1, so let's check it. When we square the denominator here, you get a 4. Same here, so we can factor out the 4. So we get 1 over 4 times square root of 5. And then we are left with the square of this numerator minus the square of this numerator. Then all we have to do is to square this term, so we get 1 plus 2 times square root of 5 plus square root of 5 squared, that is 5. And then we're going to get minus 1 squared, or 1, plus 2 times square root of 5, because we have minus, minus, and then we're going to get minus square root of 5 squared, or minus 5. So the 1 and minus 1 are going to cancel. The 5 and minus 5 are going to cancel out. We're going to be left with 2 square root of 5 plus 2 square root of 5, or 4 square root of 5. And of course, these two are going to cancel out, and we're indeed left with 1. So as strange as it looks, this is actually a closed form formula for the terms in the Fibonacci sequence. And the way we obtain this solution is using our algorithm for solving LHRRCCs. And so now you can compute the 100th term of the Fibonacci sequence simply by plugging the value 100 for n.